is when you have a beam which is horizontal, but now you are going to load it in this fashion. So imagine you are going to bend the beam. So imagine you have a member or a specimen, and rather than pushing, you are bending it. Do you agree with me? Now, if you think about this process of bending, do you agree with me that this guy is going to bend maybe something like this? So this guy is going to bend something like this. Now, top part is going to get compressed, and the bottom part will get elongated. So what's going to happen is, because you are bending, the top part or the top fibers would get compressed, the bottom fibers would get stretched. Imagine if you want to break a piece. If I want to break this, what is the easiest way to break this? Maybe apply tension and compression fluctuating. So basically, pull it up, pull it down. If I give you a stick and say I want you to break the stick, so what you're going to do is you'll try to bend the stick. By bending, what you're going to do is you're going to stretch part of the stick and you're going to compress other part of the stick. So this state creates tremendous amount of stresses in the beam, and those stresses are called as bending stresses. Now, bending stresses are nothing but normal stresses. Normal stresses. And bending stresses, there is fundamental equation of bending is given as M divided by I is equal to sigma divided by Y is equal to E divided by R, where M stands for bending moment, I stands for moment of inertia, sigma stands for bending stress, and I want you to observe this. Do you agree with me? This farthest fiber is stretched the most. So which means how far are you from this central axis, also called as the neutral axis? The stress depends upon how far you are from this neutral axis. I want you for a minute look at the figure that I have drawn. Do you agree with me that the green figure and the red figure stands for the initial position or initial state. Green figure indicates the stretch and compress state. You agree with me, both of them intersect at one point on the left and another point on the right. So if I were to draw an imaginary axis through these 2 points, essentially that plane is neither stretched nor compressed. So that plane has neither stretched nor compressed. So that is the plane of zero stress, and that is called as the neutral axis. On neutral axis, stress is equal to 0. As you go above the neutral axis or you go below the neutral axis, the stress increases. It can be compressive, it can be tensile. Bending stresses are normal stresses. Normal means they are perpendicular. And Y stands for the distance from the neutral axis. So distance from neutral axis. NA stands for neutral axis. And E, as you know, is Young's modulus. And R is the radius of bending. So depends upon how far have you bent this member. So this equation is M upon I, where I stands for the moment of inertia. Sigma or F upon Y is equal to E upon R. Everyone understood this? That is the entire chapter on bending stresses. Now, before I go to the next chapter, I want you to understand bending and torsion, they are similar phenomena. For example, if I bend like this, again I'm bending about the x-axis or I'm bending about the y-axis. This is bending about x-axis, is bending about y-axis. But if I were to bend around z-axis, that is called as twisting or torsion. So the next part is torsional stresses. Next part is torsional stresses. So when you have a torsional stress, you do not bend about x or you do not bend about y. You do not bend about x, you do not bend about y, but you bend about z. So this is the z axis. So you have torque. Instead of bending moment, you have T, which is called as the twisting moment. Twisting moment. Now, whenever you have twisting moment, I want you to think about the problem that I have posed on the top. What would bending do? Bending increases or decreases the length of the fiber. Bending increases or decreases the length of the fiber. What would twisting do? Twisting would distort the fiber. Twisting would distort the fiber, which means torsional stresses are shear stresses. And twisting is occurring about IZZ. So this same equation, what you have for bending, gets replaced, which is extremely important. The moment gets changed by torque. This I is IXX or IYY. IXX or IYY. Because please note, when you are bending about X or you are bending about Y. So the moment of inertia is about IXX or IYY. But twisting is about Z. So this moment of inertia will get replaced by IZZ. Then sigma is for the normal stress. In the case of twisting, you get shear stresses. Because think about it. When you bend, you are increasing, you are generating tension or compression. When you are twisting, you are creating shear. If you don't believe me, I want you to understand, if you take a shaft and try to rotate it, let me give you an example. Just take a rubber beam. You would notice when you twist it, you would notice the cross section get distorted. Cross section does not get elongated or does not get compressed. It gets distorted in the plane, which means you are going to get this twisting. So you have tau twisting. What would be the twisting at the center of this shaft? What would be the twisting at the center of the shaft? 0. So sort of this center line of the shaft is acting like a neutral axis. And how far you go from the neutral axis gives you the radius. So it will be R. Since we are dealing with shear stress, E changes with G and you have theta over L. So The equation for the bending stress is M divided by I is equal to sigma divided by Y is equal to E divided by R. Equation for torsion stress is P divided by IZZ, which is also called as IP, which is called as the polar moment of inertia. Why for the polar moment of inertia? Because the axes that we are referring to are R and theta. Those are polar coordinates. There we are referring to X and Y. So here we are referring by R and theta. So those are the polar coordinates. So this IZZ is sometimes called as IP, which is the polar moment of inertia. Normal stress get replaced by shear stress. R is the radius. G is the shear modulus. L is the length of the shaft. And theta is the angle of twist. Do you agree with me? That's your one chapter on bending stress. That is another chapter on torsion stress. Did you understand this? Now, one thing I want you to understand, if I want to think about simultaneous action of bending and torsion, so let me pose this problem. You agree with me, the bending stresses are going to give rise to normal stresses. Twisting is going to give rise to shear stresses. Normal stress is perpendicular to the area. So now I want you to think about this specimen. So what I'm trying to see here is, if I have a specimen, do you agree with me? The normal stress will be somewhere here, but the shear stress will be on the surface. So normal stress and shear stress are perpendicular to each other. You agree with me? Because we have a specimen, normal stress is going to be perpendicular to the area, shear stress is going to be the parallel to the area. What happens when you have normal and shear stresses acting together? What happens when you have normal and shear stresses acting together? Huh? You basically get something else. Imagine in statics, we talked about one force acting in the horizontal direction, one force acting in the vertical direction. So the resultant force was acting at some other direction. You agree with me? So when I had vertical force, when I had horizontal force, both of them got added vectorially. So basically we added with the vector addition and the resultant was something else. Give an example. 3i plus 4j gave me the total value of resultant vector 5. So 3 kilonewton force in x direction, 4 kilonewton force in y direction gave me a 5 kilonewton force which was at 36.5 degrees. Remember that? So principal stresses, they are the resultant of the normal stresses and shear stresses acting together. So whenever you have only normal stresses acting, you get tension and compression stress. When you have only shear stresses acting, you get shear stress. But principal stresses come in the picture when you have simultaneous action of normal and shear stress. You agree with me? We'll derive the equation for principal stresses maybe after a few classes. But these two are your next couple of chapters. So this gives you about 80% of mechanics of material. The first part is compressive stresses, tensile stresses, stress strain curves, Poisson's ratio, Young's modulus, shear modulus. This is the first half of the mechanics of material. This is remaining 30% of mechanics of material, which is the bending stresses and torsional stresses. Please understand the structure of the equation is the same. Bending moment, twisting moment. Moment of inertia about x, moment of inertia about y, moment of inertia about z. Bending stress, which is normal stress, gets replaced by the shear stress. Bending stress is dependent on how far you are from the neutral axis, the axis which is neither bent or not compressed or not stretched. Shear stresses is dependent on how far you are from the center line, the center axis. Bending is a normal stress phenomenon. So what you have is you have E, which is the Young's modulus. Shear stress is nothing but the shear phenomenon. So you have the shear modulus. The only thing that you have division by radius, and this basically gives you the twist per unit length. So you are dividing by something called as length per twist. That's the only difference. Everyone understood this? Because you are bending in this plane and you are twisting in the other plane. So we need to find out what is the twist per unit length. That is what is giving that equation. Everyone understood this? So let's work out some problems. Okay. The beam is supported by two rods, rod AB and rod CD. The beam is supported by two rods and they have cross-sectional area of 12 millimeters square and 8 millimeters square. So this cross-sectional area AB is 12 millimeters square. This cross-sectional area is 8 millimeters square. If this distance is 1 meter, we need to find out average normal stress in each rod. So we have to find out what is the stress in AB, and we have to find out what is the stress in CD. I want to make this problem even a little bit more challenging. If the length of each rod is 1 meter, Young's modulus is 200 kilonewton per meter square, which is 200 into 10 to the power 9 Newton per millimeter square, kilonewton per meter square. Tell me the so that's okay. We will so then we can try to find something else. Let me solve this basic problem first. The beam is supported by two rods AB and CD that have cross-sectional areas 12 millimeters square and 8 millimeters square. If the D is equal to 1 meter, what is the average normal stress in each rod? Now imagine once there is this load of 6 kilonewton, this is 6 kilonewton going down, and I want to find out the reactions RA and I want to find the reaction RC. I want to find out the reaction RA and want to find the reaction RC. If I draw the free body diagram of the rod, you agree with me this RA would be in this direction, this RC would be in this direction. Why do I get these reactions? Because please understand, I've separated the string AB by and then actually I have cut it at A, so these reaction forces came into existence. As soon as I combine these together, the RA going down and RA going up will get cancelled. So this is 6. So I'm first going to apply summation of forces in y direction is equal to 0. So I get 0 is equal to plus RA minus 6 kilonewton plus RC. So this equation becomes RA plus RC is equal to 6 kilonewton. Now, how do I find out the value of RA or RC? So I take summation of moment about A is equal to 0. So curl your fingers in the direction of moment. This distance is 1. This distance is 2. Now, I want you to have a little bit of insight into the mechanics of material problems. Can anyone tell me, looking at the figure, and let me draw this figure a little bit nicer. Can anyone tell me, looking at the figure, this is 1. Whether RA would get more load or RC get more load. Now the problem that I want you to understand is trying to give me the answer without calculating. You agree with me that this 6 kilonewton is closer to RA. Imagine a case where this 6 kilonewton is on RA. If this 6 kilonewton is on RA, what would be the reaction at RA? 6 kilonewton. Do you agree with me? Everyone understands? If this 6 kilonewton was here, the reaction at RA would be 6, but the reaction at RC would be 0. Do you agree with me? If this 6 kilonewton would have been on the way up to RC, what would be the reaction at RC? 6. Imagine if this 6 kilonewton would be at the center, what would be the reaction RA? 3. What would be the reaction RB? 3. Now, can you see that this 6 kilonewton is 1 meter from here and 2 meters from here? So, without writing the equation, tell me what would be RA and what would be RC. RA should be 4.5 or 4? RA should be 4 and RC should be 2. Everyone understood this? If you understand this, then you can solve traveling load problems. So which means imagine a case where that load is traveling from point A to point C. What? It's like walking over the bridge problem. So basically, or the cars traveling on the bridge problem. Imagine this is a bridge and the car is traveling from point A to point B. So that is called as a traveling load problem. But the principle is the same. So now what you have is, I will just write this down. RA, assuming everyone understood, RA is equal to 4 kilonewton and RB is equal to 2 kilonewton. Do you agree with me? Okay. Now, how do I find out the normal stress? Now, I know the value of Ra, I know the value of Rc. Sigma AB is equal to Ra divided by area AB. What is Ra? Ra is 4 kilonewton, 4 into 10 to the power 3. What is AB? Is 12. So I get this Newton per millimeter square. Do you agree with me? Sigma BC is equal to RB divided by area BC. RB is 2 kilonewtons divided by 8 Newton per millimeter square. Everyone understood this? Now I want to ask you this question. I have given you the length of this beam, length of this member. This is 1 meter. This is also 1 meter. I have given you the Young's modulus. Can someone tell me the elongation of the member? How far AB would be stretched and how far CD would be stretched? Can someone tell me value of sigma AB? Sigma AB. Can I tell me sigma BC? Tell me sigma AB and sigma BC real quick.
AB is 333.33.
333 megapascal. 333
333.
Newton per millimeter square. And here 250. Now what I'm asking you to tell me is, I'm asking you what is the deflection AB and what is the deflection BC. How would you proceed? I gave you set of equations. Remember, that is entire mechanics of material. Tell me which equation would you use? Yeah, you will try those. Nothing.
Becomes small equation, so equals sigma.
Correct. So the equation that you would use is E is equal to sigma divided by epsilon. Do you agree with me? E is given to you. Sigma is found out, right? So you can find out 200. Now it is kilonewton, 10 to the power 3. I need to convert it into, okay, I need to write this down. So this is Newton per meter square. But check this out. My stress is in millimeter square. So to convert meter square into millimeter square, I need to divide by 10 to the power 6. Which means I need to multiply this by 10 to the power 6. So my Young's modulus is going to be 200 times 10 to the power 9 Newton per millimeter square. I want you to look at this. So this guy meter is equal to 1000 millimeters. Do you agree with me? So if I want to convert this equation, so I get 200 into 10 to the power 9 Newton per millimeter square. And then what I do is I use this equation. E is equal to sigma divided by epsilon 200 10 to the power 9. Sigma is 333 and epsilon is nothing but change in the length divided by original length. So I get delta divided by L, which is 333 divided by 200 10 to the power 9. And we need to find out the value of delta, but value of L is given to us. So delta is equal to 333 divided by 200 10 to the power 9 multiplied by the length, which is 1000 millimeter. So once again, I explain this problem. First, we found out the value of sigma. Sigma AB is 333. We found out the value of sigma BC, which is 250. Now we have to find out the elongation. Elongation is change in the length. Anytime you come across elongation, compression, like increase in the length, decrease in the length, you have to use the strain equation. What quantity relates stress and strain? It is the Young's modulus. So I am using the equation Young's modulus is equal to stress divided by strain. I substituted the value of stress, substituted the value of Young's modulus, and that gives me the strain, delta over L. Now I need to find out the elongation, which means I need to multiply by the length, original length, which is 1000. So now I got how far that AB is stretched. Do you agree with me? Same thing, I'm going to do it for BC. For delta BC, I would say 250 divided by 200 10 to the power 9 multiplied by 1000, and now I would get the deflection in millimeters. Yeah. Yeah. So I just gave you the value of E. So assume the value of E for the material to be 200 into 10 to the power 9 Newton per millimeter square. This is given. This is given. So I try to give you in, so ignore this. Imagine I gave you the value of E for this material, 200 10 to the power 9 Newton per millimeter square. And then that gives you the value of millimeter. Okay. Next problem. Now in this problem, what you have is you have an eye bolt. And that eye bolt is held together with this nut. And now what you have is you have this eye bolt. So I'm going to draw this eye bolt. I'm going to draw this eye bolt. And this eye bolt is held in piece with a washer, and then there is a nut. So you have this nut, and you have this eye bolt. Now we have to find out the diameter of this bolt. We want to find out the diameter of this bolt. The load that is acting on this bolt is 5 kilopounds, so 5,000 pounds. and the normal stress is 21 KSI. So sigma is 21 10 to power 3. KSI is kilopounds per square inch. So LB inch square. So what I need to find out is what is the diameter. This is like a design problem. What is the diameter of this bolt so that the bolt can sustain 5,000 pounds, and sigma value is given as 21 10 to the power 3. Sigma is equal to P divided by A. So 21 10 to the power 3 is equal to P, which is 5,000, divided by A. It's a circular bolt, so pi by 4, D square. Solve this and find the value of D. Find the value of D in inches. Everyone understood this? Now I want to ask you one more question. Imagine my bolt is strong. My nut here, that I'm shown here, is also strong. You agree with me? There is a possibility that horizontal support could fail. You agree with me? How would this horizontal support fail? Now, what I want to do is I want to show you the three-dimensional picture. Okay, so what you have is you have this support here. You have this bolt. Here you have this bolt. Under the bolt, you have this washer. Okay, you have this washer. Under the bolt, you have this washer. And this bolt is protruding. So you see the bolt here. You see the bolt here. Okay, this is the bolt. Now everything is strong. So you pull this. Do you agree with me? It is quite possible that this washer could shear off the plate, which means what will happen is this whole thing will come down. So you will have this whole piece coming down, and basically if you look at the top part, now if you look at the washer, so if you look at this, there will be a big hole here. You agree with me? So what you are going to have is you are going to have the failure on the perimeter of that bolt, a perimeter of that washer. This washer failure is called as circumferential shear. So please try to understand. I want you to visualize this. If you pull the bolt, it is quite possible that the bolt may break here. It is also possible that this washer could shear this piece off. So this piece, if you look from top, is something like this. So it can fail in a circumferential shear. So if I want to look at the circumferential shear, that area is again P divided by A circumferential. Area is going to be 5,000. If you open this strip, this strip is going to be pi times D multiplied by this thickness, which is H. So tau, this would be pi times diameter of this washer, which is 1 inch, multiplied by the height, which is h. And the shear stress is going to be 5 ksi, which is 5 into 10 to the power 3. So the only unknown in this equation is h. So I want you to understand this is kind of a design problem. You have this eye bolt and you are pulling this eye bolt down by 5 kilograms. It may so happen that the bolt itself may break. It is also possible that that material that you have that is supporting the bolt could get shear off. And in that case, it could be a circumferential shear, which means this whole washer would pull this whole thing down. Are you able to visualize this type of failure? The whole thing goes down. And that would give you the value of height. Everyone understood this? There are two types of failures. This failure is purely tensile failure. And this failure is nothing but circumferential shear failure. Any questions? Okay. There is one more failure, which is what could happen is this bolt can crush the material. So basically, the bolt crushes into material. So whenever you see the bolt getting stripped, when the bolt, you can spend a lot of time on this. So these are the threads. What happens is when you have the threads, what do you mean by thread stripping? That thread stripping behavior, which means this thread comes off from here. So what you need to do is you need to find out the area of that strip, multiply that by the number of bolts, and that gives you the stripping strength of the bolt. There is also failure within the nut and the bolt, wherein what happens is the threads shear off or the threads crush. So there are at least 5 different types of failures that you can use to design this nut and bolt assembly. But in the context of mechanics of material, since they have given us the shear stress and they have given us the tensile stress, these are the 2 failures that we are considering. Everyone understood this? So, okay. Next problem. I'm going to give this problem to you as a homework, but I want you to understand this problem can be solved. We already have solved this problem. So this is FAB and you have FBC. So what you have is you have this vertical force. This vertical force is supported by an inclined force, and the cosine component of this inclined force is supported by this force. So what you want to do is you have this P, this is angle theta, this is FAB, and you have FBC. So what you do is you apply summation of forces in y direction is equal to 0. This x is y. Summation of forces in y direction is equal to 0. So you would say minus P plus FAB cosine theta is equal to 0. Find out the value of FAB. Sigma AB is equal to FAB divided by area AB. Then you apply summation of forces in x direction is equal to 0. So what you have is 0 is equal to FAB sin theta minus FBC. Thus FBC, since FAB is known, you can find out the value of FBC. Sigma BC is equal to FBC divided by area BC. Are you with me? So you can find out the value of theta, because please note this angle is given to you. So this theta is equal to tan inverse of 4/3. Can somebody tell me what is tan inverse of 4/3? 53. Huh? 53, yeah. Then you will substitute that 53 in this equation. P is given to you as 60 K. So you can find out the value of P. Value of sigma AB, you can see it is given as sigma fail as 400 with factor of safety of 2. So sigma AB is equal to sigma BC is equal to sigma fail divided by factor of safety is equal to 200. So sigma AB is equal to 200. Sigma BC is equal to 200. So this should be able to give me value of area AB and area BC. I will repeat this problem again so that everyone understands. In this particular problem, what you have is you have a load that is supported by two members. One is a horizontal member, BC is a horizontal member, and AB is an inclined member. What they are giving us, they have given us value of failure stress. Failure stress is 400 megapascal. Mega means 10 to the power 6, which means 400 megapascals. Sigma is 400 megapascals, is nothing but 400 Newton per millimeter square. 400 Newton per millimeter square. So this is the failure stress. Factor of safety is 2. So the allowable stress is 400 divided by 2, 200. We don't want to go to 400 level. We want to give ourselves some margin of error. So our stress, we are going to limit to 200. So 200 is the maximum stress that we can let induce in bar AB and bar BC. Everyone understood this? Now the external force P is 5,000 or 60,000. So external force is 60,000 newtons. Now I want to find out, because of that external force of 60,000 newtons, how much of force I'm getting in member AB and how much of force I'm getting in member BC. You agree with me? So for that, I have to use the God equation for statics. So I applied summation of forces in y direction is equal to 0, and I got the value of FAB. What is the value of FAB? Yeah, 60,000 divided by cosine 53. That should give you the value of FAB. Once I know the value of FAB, I substitute the value of FAB here. Sigma AB is 200. Get the area AB. You agree with me? Area AB is 5/4 diameter of AB square. So you can find the diameter. Everyone understood this? Same thing you will do for BC. So FAB sine theta is equal to FBC. You can find out the value of FBC. And again, the stress is 200. So you can solve for area BC, and from area BC you can find out the diameter. Everyone understood this? The next problem is, this is the quarter joint problem. So what you have is, you have a quarter pin, and this quarter pin is holding, this is called as socket. It's called a socket, and it's called a spigot. So this quarter pin is holding this socket and spigot together. So they are asking us to find out what is the size of the diameter, what is the value of D. And please understand, if you have the loading, it is supposed to sustain the loading of failure normal stress is 30 kilonewtons. So the P is 30 kilonewtons. So P is equal to 30 kilonewtons. So if this pin is supposed to hold 30 kilonewtons, this 30 kilonewton load will be supported by this cross section. So P sigma is equal to P divided by A. This failure is going to be a tensile failure, which means I need to find out the tensile stress. Now notice here, the tensile stress, normal failure stress, is 500 megapascals, but the factor of safety is 2.5. So sigma is 500, which is the ultimate stress or the yield stress, divided by the factor of safety 2.5 is equal to 30 kilonewton divided by area, which is pi by 4 D square. Solve this equation and get the value of D. Solve this equation and get the value of D. Now I want you to understand, how is this quarter joint, how does this joint look? So please understand, what you have is, you have this socket. You have the socket, and in this socket you have this hole for the quarter. Now this socket fits into a spigot. So this socket fits into a spigot. This is how the spigot looks like. So what happens is, this socket you put inside the spigot. The spigot also has a hole on top. The spigot also has a hole on top. And what you do is, you take the quarter and hammer it in. So you have this spigot that is holding, spigot goes inside the socket. This hole and this hole is aligned, and on top you have this quarter. The quarter is actually a taper quarter. So the quarter goes in, and then you hammer it down, so that because of the interference split, quarter remains in between spigot and socket. Everyone understood this? I want you to understand, if I pull this super duper hard, can you visualize that there is a possibility that this quarter which is supposed to go all the way in, could fail in double shear, which means what can happen is the top part of the quarter would remain as is, center part of the quarter would remain in socket and spigot, and the bottom part of quarter would get separated. So which means this quarter would shear off at this location and shear off at this location, as if this socket would shear that quarter off. Everyone understood this? So this is a double shear failure. You agree with me, the quarter is failing at two joints or two areas. So if I want to find out the thickness of the quarter joint, if I want to find out the thickness of the quarter joint, this guy is the thickness. This is given as 10 millimeters. It's given as 10 millimeters. So load again is going to be the same, but the area would be the double shear area and then you are going to have tau design. Now check this out. The tensile, in the shear failure happens at 375 and the factor of safety is 1.75. So this equation is 375 divided by 1.75 is equal to P is 30, 10 to the power 3. Since it's in double shear, this will be 2 times 10 times T. 10 times T is the area. Since there are two areas, this is the area. Since there are two areas, one on top and one on bottom, you multiply by 2 and from here find out the value of T. Everyone understood this? Just pay attention to this problem. This is a very important problem. And this is the design problem. Any questions? No questions? Okay, the next problem is exactly similar to the problem that I have solved. So I'm going to give it to you as homework. 773. Then this problem again is exactly similar to the problem that I have solved. The only change here is this guy kind of pivots. So since it's a hinge, this guy is going to pivot. But please note, theta on the right and theta on the left is going to remain the same because this is going to pivot. So when you have theta remaining the same, once you multiply theta by the radius, in this particular case 300 and maybe in this case 500, that should be able to give you the deflection of that rod. So let me solve this real quick. So what you have in this problem, you have this lever. This lever is attached to at CD, CG and DF and AH. This angle is 2 degrees. So what I want to do is I want to find out the deflection of point A. I want to find out deflection of point C. And I want to find out deflection of point D. So since this is 2 degrees, delta A is 2 degrees. And remember, whenever you are multiplying r times theta is equal to delta, this theta must be in radians. You cannot use this theta in degrees. Whenever you are trying to find out the delta, so give an example. So this distance is delta. This distance is r. This is delta.
So you have to find out using R times delta. So R is 200, delta is 2 divided by 2 divided by 180 times pi. That gives you the value of delta A. Delta C is, please note, it is 300 multiplied by 2 divided by 180 times pi. And delta D is equal to 500 multiplied by 2 divided by 180 times pi.
And you found out the deflections at delta A, deflection at delta E, deflection at delta D. You know the original lengths.
So you know the length of AH, which is 200. So you can find out epsilon AH is equal to delta A divided by 200. Epsilon CG is equal to delta C divided by this 300, and epsilon DF is equal to delta D divided by 300. So this is epsilon, epsilon, epsilon.
Everyone understood this? So you have that horizontal lever. You rotate that horizontal lever. The only way you can rotate that horizontal lever if AB is stretched, CG is stretched, and DF is stretched. Do you agree with me? You pull the lever like this, and all these ropes will get stretched. By how much amount would they get stretched? The stretch would be the radius multiplied by the angular deflection. You agree with me? The stretch is going to be equal to radius times the angular deflection. So if you take that stretch and divide that by the individual lengths, what you get? Strain in each wire. You agree with me? Everyone understood this? Let me ask you the next question. What would be the stress in each wire? What would be the stretch in each wire? What would be the stress in each wire? If I give you Young's modulus, you multiply the strain by the Young's modulus, and then you get stress. Remember, Young's modulus is stress divided by strain.
Young's modulus is stress divided by strain. You have found out these strains values, right? So I give you Young's modulus, maybe 210 to the power 9 Newton per millimeter square for that material. You multiply those strains by the Young's modulus, and you get the values of stresses. Do you agree with me? And that is how so these are the same type of problems. Again, exactly similar problem. So I'm going to give it to you as homework. This problem I want to solve though.
So what you have is you have this rectangular element. Okay, rectangular element means the angle between each edge is 90 degrees. So it is like this. You are applying
Shear loading. So you apply the shear loading, which means you apply load here. Then you agree with me that under the action of shear load, this element would get distorted. Do you agree with me? The angle with which that element is getting distorted is the shear strain. So how much is the distortion? Can you see? Let me draw this. This is like this. And then this is getting distorted by 3 millimeter. This length is 400. So if I want to ask you, what is this angle? This angle is nothing but 3 divided by 400 in radians. Do you agree with me? If you don't believe me, find out tan inverse of 3 divided by 400, multiply that into radians, and verify that this answer is 3 divided by 400. And this distortion here is 2 millimeters. So this distortion here is 2 millimeters. This distance is 300. So this angle is 2 divided by 300. So the total distortion, the shear strain, is nothing but 3 divided by 400 radians plus 2 divided by 300 radians. You agree with me? You have this block. You are applying shear stresses on this block. This rectangular block gets distorted and becomes like a parallelogram. And what you want to find out, what is the angular distortion. The angular distortion is nothing but the distortion here and distortion here. You agree with me? The stop distortion is 3 millimeters divided by 400 radians. 3 millimeters divided by 400 radians. The bottom distortion is 2 divided by 300 radians. So the total shear strain is nothing but the vertical distortion and the horizontal distortion. Everyone understood this? Now I given you shear strain. If I ask you what is the shear stress, how would you tell me? You would need one more quantity, that is shear modulus. So you take shear modulus G and multiply this by this gamma and you get the shear stress. So key observation here, Young's modulus is normal stress by normal strain. Shear modulus is shear stress by shear strain. Everyone understood this? Next problem. This is the exact same problem as the bolt problem. I'm going to give this as homework. It's exactly the same problem as the homework bolt problem. This is also the same problem as the bolt problem, homework, and this is actually the bolt problem. So homework. Everyone understood? Okay. Let me work out some problems from the next chapter. Next chapter deals with Young's modulus is equal to stress divided by strain. Remember, I talked about the stress and strain curve for the mild steel, wherein what you have is you have this specimen, you grip this specimen in the jaws of the tensile testing machine, and you pull, you apply vertical loading, and you measure the load and the deflection. Sometimes you can actually, instead of pulling, you can also push So you can actually push it down. You can push it down. So you can measure load versus contraction or load versus deflection. So whenever you have load and contraction or load on elongation or load versus deflection, divide all the loads by the initial area. What do you get? Load divided by area, stress. So you would get all the stresses. You get stresses here and you get strains over here. When you divide this contraction by original length and you divide this load by area. Then what you do is you plot this onto stress versus strain curve. And once you plot it versus stress versus strain curve, the slope of the straight line gives you the Young's modulus. Are you with me? So imagine you are performing an experiment. In this experiment, you have the tensile testing machine, you load the specimen and measure the load versus deflection. Get the value of that load, divide that by area. So you are going to get stresses. Can you see the load divided by area? You get stresses. Initial length is given to you. So you are going to get deflection divided by initial length. You are going to get strain. You agree with me? Then you are going to take a graph paper and then plot stress versus strain. And you will see the stress versus strain would be something like this. The first region of the stress strain curve would be a straight line. You find the slope of that line, and that is the Young's modulus, which is stress divided by strain. Everyone understood this? This entire chapter deals with these problems. You are given the value of stress, you are given the value of strain, you use the graph paper and plot these values. And slope of this straight line is the Young's modulus. And as I discussed in last class, the area under the straight line is the energy stored. This is energy stored. This is energy stored. Next problem, same problem, stress versus strain. And then you will know that this is the ultimate stress. This is the lower yield point, upper yield point. So all this deals with our next chapter, chapter 8, deals with how do you analyze the experimental load versus deflection data. Again, you can go through all these problems. They are exactly same as the problems that I discussed in class. In next class, I'll try to work out a few problems and then we will stop. We'll move on to the next chapter. With that, I'm going to stop here.